So the next type of exponential function that we need to work with is with a function that actually has an irrational base as opposed to a rational base. So everything that we've dealt with up until this point has been with 2 to the x power or some other base to the x power. Now if you look here at this first little paragraph, you'll look and see an equation y equals 1 plus 1 over x raised to the x power. Now what you may be thinking to yourself is that looks very similar to the compound interest formula, except you don't have the rate and a number of compounding periods and you don't have a time with it, but it's very similar setup. Well, if you were to graph that particular function right there, what you would end up with is you would end up with an asymptote that is approximated at about 2.71828. That number is what we call the irrational number E. E is used in a lot of science and business calculations when we want to get a continuous growth or decay value. And so we tend to call E a natural base whenever we use it in exponential functions. And so this is going to be our next part that we're going to work with exponentially. And so in the previous lesson we dealt with compound interest. Well, we can now use E to figure out a continuously compounded interest. So before we were talking about maybe doing it monthly, quarterly, daily, and we were breaking our annual interest up into those individual payment parts. Now what we're basically going to be saying is that we are going to continuously put the interest right back into the account every second of every day. And so since we have computers, this is much easier to do. And if you look at this little summary box of comparison of a $10,000 investment account at 12%, you can see the different values that happen as a result of different compounding features. If you notice, with each increase in compounding all the way up to continuously compounded interest, that the jumps in the value become less and less, and they get closer and closer and closer. So you would think that the more you compounded something, the more it would jump up in value, and it actually has that reverse effect. It has that leveling off of the value. And so we can actually come up with a compound interest formula that is using the E as a natural base, and it's the continuous compound interest formula that you see right here. So now we're taking the principal and we're multiplying it times E raised to the R times T. So this is slightly different than the compound interest formula that we're using for continuous compounding. And so whenever you read a problem like sample problem number 5, you want to be very aware if it's asking you to compound monthly, daily, annually, or is it asking you to compound it continuously. And so once you see continuously, you'll know that you'll need to move to a different formula. So go ahead and try sample problem number 5 right now. This is something that you should be able to do pretty comfortably, and we'll look at that in just a second. Okay, so if we look at the problem here, we see that we have a beginning balance of $3,000, and so I'm just going to plug this into the formula. Our principal balance is $3,000. We have a base E. We're raising it to the R, the rate of 0.05, times the number of years, and it's asking us to do 4 years later. So that is my calculation that I need to put into my calculator. So let's look and see how that works. So we have 3,000, and E is to the left of the number 1, and it says e to the x power. So we're going to actually say e to the x power, and it presets our exponent for us. And now we can say 0.05 times 4, and we hit enter, and we see $3,664.21. If we look at the problem, however, it asks us to round that to the nearest dollar, so we would simply say $3,664. And that's a pretty good straightforward problem to learn continuous compounding. Alright, very good.